Do we have a name for this show? This is in the series of We're Fucked.
Yeah, it is another. It's a sequel. It's, I think, volume 5 of How Fucked We Are.
It's actually volume 4. I was looking to see the other ones we had, but still, yeah.
Well,
it's okay.
It feels like 5 because we're so fucked.
We're twice fucked sometimes, so. Okay, started recording, so I guess at some point we could start.
All right.
Because that's how this goes, as far as I know.
Hello and welcome to Science in Context. Today we are back talking about a little climate change related stuff like we've done a few times in the past. We wanted to talk a little bit about weather and how it's related to climate change and how it's not related to climate change. So, yeah, Mike and I are here. Had a very climate change heavy last probably few months with our episodes, huh?
Yeah, we've had at least like 3, right? We did the one on the permafrost, which is sad, and we'll definitely talk more about that at some point because it's actually a little bit related to something I have here. And we talked about geoengineering, ways to fix this. Not really fix, but kind of help out. And now we're here, and it's like the 3rd one in 2 months. It's a really important issue, so we might as well cover it.
I think one of our first ever episodes was about climate change, way back. So yeah, it's important. It's important to both of us. It's important to the world. So today we wanted to talk about weather and some of the kind of misunderstandings, or at least one of the main misunderstandings about climate change, and that when you have cold weather, it might seem like, because the other word for climate change, the other phrase for climate change is global warming. And when there's cold weather out, people say, well, how's it cold out when it's global warming has been happening for the last however many years? So the thing that, like, the main takeaway would be that weather, like instantaneous weather, can't confirm or deny climate change. Climate change is really studying how the weather changes over decades or over hundreds of years even. So individual extreme weather events can't really confirm or deny climate change. Despite that, extreme weather events are correlated with climate change in that you have more extreme storms, more extreme cold snaps, some of the hurricanes that we've seen in recent years. You can't necessarily prove that they're due to climate change, but the higher intensity and the more common incidence of those things is linked to climate change. And there's evidence pointing to climate change being responsible for a more frequent occurrence of extreme
that's one
weather
of those
events.
things that makes it a lot harder to communicate, I guess, kind of the urgency and like the bad things that are happening with climate change. It's hard to say, like, you can't really say this storm was caused by climate change because it's too complicated, but you can say that it happened more frequently. I mean, this is something that happens in science in general. It's hard to make definitive statements sometimes, especially when it's about a complicated system like the weather. So we can't just blame a single hurricane on climate change, but we could say climate change helps to make these storms like happen more frequently or be more destructive and stronger when they happen. Yeah,
exactly. And it's kind of a human condition thing where we live in the moment so much, and everything's concerned with the here and now and the present and even maybe the near future. But it's difficult for people to take something like climate change that's really hundreds of years in the making, ever since the Industrial Revolution, where we started using a lot of fossil fuels and putting a lot more carbon into the atmosphere. That's accelerated this heating up of the planet, and it's even though it's accelerated it, it's really taken hundreds of years for it to really manifest itself in concrete ways like we're seeing now. And part of what you mentioned, I kind of want to, like, I guess, provide another example of something. So how slow it seems that we are to respond to climate change, because scientists have been saying, hey, this is dangerous. We're pretty sure that we can't prove anything, but it seems to be tied to these weather events, and it seems to be tied to rising sea levels and all of that. It kind of reminds me of something like cigarettes and how dangerous they started to seem to be 50 or 60 years ago, but still people were like, whatever, I like cigarettes, I'm going to keep smoking them. And so it kind of reminds me of that, where it takes a long time for science to really definitively show people that they need to change their behavior for the benefit of their own health.
Yeah, it's one of those things that's just so tough to tell people about. And actually, do you think this would be if we go back a little bit to talking about how like you can't assume like something about the climate based on like one day or one season. It's more about the long-term trends. It's kind of like something I think we've talked about before, but in statistics, where you need multiple points. You can't just take like one data point and say that this is exactly what you need. You need like a large sample size, and in this case, it's a large sample of time. And so, like, well, average temperature 10 years ago was a lot colder than it is now, and then also like 20 years ago was colder than it is now. It's more like you need lots of data points, basically. You can't just think about one season. It's like, well, it happened to be extra cold, because that's not really what I guess the term climate change really means.
Right. Yeah, I mean, one way to kind of demonstrate it is that I had a chart that I was looking at. Let's see if I can find it. I don't know where it is. I have a million tabs open, but basically it was showing the number of seasons that were surprisingly warm or surprisingly cold over time. And like back in the late 1800s, there was a lot more surprisingly cold seasons, and over time it's gone to way more surprisingly hot seasons up till modern day. So it's just another one of those trends that's showing that, you know, if you look at the big picture, if you zoom out and you say, okay, what's happening over time? You have global temperatures rising, you have surprisingly hot seasons happening more frequently, rising sea levels, all of those things. So anyway, to kind of get to a very pressing issue, there's the polar vortex that's happening in the Midwest of the United States right now. It's kind of one of those things where I think even President Trump tweeted about something about how global warming might be helpful for this polar vortex, which, again, single weather event does not correlate or does not prove or confirm or deny climate change overall. But I kind of want to talk about how this polar vortex it kind of happens and how it might be even linked to climate change a little bit. So, Mike, have you heard of the jet stream before?
Kind of. I don't really know what they are. I just know that they exist, and I've heard about it on the weather.
Exactly. Every time when you're watching Al Roker do the weather, you can see this
exactly.
kind of curvy S-shaped thing going across the country that's the jet stream. And I think they call it that because planes use it to speed up their travel. Don't quote me on that. I didn't actually look into that. What I looked into is what it actually is, and it's essentially these westerly air currents. So westerly means it comes from the west and moves towards the east, and it's caused by both temperature gradients and the Earth's rotation itself. So if you think of the Earth rotating, we rotate, if you're looking at it at the United States, it's going to the right? So like it's morning in New York when it's not quite morning in California yet. So it's moving to the right. And so the Earth rotating that way is pulling the air currents due to gravity. And so the air currents kind of start whipping up and pulling into these air currents. And then when there's boundaries between really cold air and really hot air, that's where you have jet streams. There's actually a jet stream in the southern hemisphere as well. I think there's multiple, but the main one that we're talking about, the one that you see on the weather report, is this main gigantic boundary between really cold and really hot air. And so what we're seeing with the polar vortex is the jet stream path is warped a little bit, and it kind of has to do with moisture in the air and how, I guess you could kind of think of it how there's different heat patterns than there used to be due to climate change. And so in the Arctic, for example, there's a lot more moisture in the air because it's a little warmer in the Arctic, and so that kind of pushes the heat further down. But it's not heat essentially because it's still Arctic air. It's still really cold, but it's warm enough to push the jet stream path further south. And so it's south enough now where it's below Chicago and below Minnesota and those areas up there that are experiencing this extreme cold right now. And so jet stream essentially traps these air pockets inside of itself. So I think even Atlanta actually Atlanta had like record low temperatures in the 30s or something like that, which seems crazy for Atlanta. Anyway, so this really cold Arctic air that moves down because it's warmer than it usually is still really cold, and it's trapped in this jet stream air pocket. And so that's where you have this polar vortex over the sort of northern Midwest of the United States. So how did that kind of make sense as far as how the polar vortex forms and how it's related to the jet stream?
Yeah, I'm trying to visualize it, and it's just like a
Yeah,
complicated thing to think about in my head. But I
definitely.
mean, essentially, you're saying is the polar vortex is able to trap basically, or is like composed of cold, really cold air, but
Yeah.
due to warming, it's been able to shift. It can, I guess, it seasonally shifts, so it's like not. It's not like a permanent shift. Is it like a yeah? Is it a permanent shift, or is it something that shifts based on just some weather event, and then it? I guess we have this big cooling in the like the United States and such. So is it
I
just
guess
like
so.
over weeks, or what's the time scale? I
Uh,
guess.
I think probably weeks to months because I think it's a seasonal shift. And so I guess another way I could explain it is the warming at the like up in the Arctic. Whenever air warms up, it expands. That might be something that we've mentioned on the show before. But usually, when a fluid warms up, it expands. So that expansion is what's pushing the jet stream further down. And so this barrier, the jet stream is this barrier that kind of traps cold on one side and heat on the other side. This cold air that's expanding because it's slightly warmer. It's kind of a confusing way to say it, but it's this Arctic air that's really cold. It's still a little bit warmer than it was, and so it's going to expand and push its way into the jet stream and push the jet stream further down. But the jet stream is still this barrier, and so it's still going to trap that cold air
Okay.
in that region.
I got you. Okay, that makes sense. And
Yeah.
so this is, would it be safe to say this is an example of it's a local weather phenomenon that's the temperature kind of doesn't have anything to do with it. Oh, it does apparently because it's due to this warming, but
Mm-hmm.
the local temperature just varies so much, right? It's just it's a different thing than overall climate change, kind of.
Yeah, definitely. Yeah. So you can kind of like this is basically making a case how global warming can kind of contribute to a certain single phenomenon like a polar vortex, because the warming of the Arctic is obviously a hallmark concern of climate change. Um, but yeah, like you said, the local temperature is dependent on a bunch of different things, and there's more that goes into it. So I guess the main point is that even though it's really really cold, it's still kind of related to how climate change can affect even something like random as like the jet stream, and sort of the borders and pockets of air that move around about the Earth and affect cold weather and affect the day-to-day weather like we're seeing in the Midwest, for example, right now.
Question is, I don't know if you've come across this in your research, but do you know if this is something that's supposed to happen more often? Because I know the Arctic is actually, it's warming up at a increasing rate, a rate that's higher than like the lower latitudes, like towards the equator, is warming slower than at the higher latitude. So is this something that would happen more often, just because the Arctic's getting warmer at a faster rate? Not really sure. I mean, it's really complicated, so obviously it'd be hard to make definitive
Yeah,
statements about these things.
I think in one sense it's really hard to project and forecast. I saw one video that I was watching yesterday that was saying that extreme cold weather events are likely to get rarer as climate change accelerates, um, but that you can never really rule them out entirely because there's always different forces that lead to cold weather events. So yeah, it's really confusing because on one hand, warming up the Arctic makes this air expand and push further south, and then you have this cold air sitting on top of the Midwest, for example. But if the Earth continues to warm up, then it's less likely that you'll even have cold weather events in general. So I don't know. It's hard to again, it's hard to project what's going to happen.
Yeah, it's a super complicated system. The weather. It's the reason
Yeah,
why we're not super accurate about all these predictions. It's just
yeah.
too many variables.
I think that's part of the problem with convincing people to how serious it is that like you can spend a bunch of time talking about how the Earth's getting hotter, and then all of a sudden there's this just insane cold snap, and trying to explain how. I mean, I can't even really explain how on one hand it could be linked to climate change, and the other hand it might not be, and on the third hand it's not even sure whether it's going to become more rare or less rare moving forward. So yeah, there's just so many different variables, and it makes it difficult to kind of persuade people that climate change is important, but it clearly is. Something I wanted to mention, I guess this probably would have been better to mention before. when you have warmer winters versus colder winters, it's dependent on not just the Arctic phenomenon that I was mentioning earlier, but also different pressure systems. So when you have like a warmer winter that happened, I think I remember the winter like 2011, 2012. That winter was unseasonably warm. I was living in St. Louis at the time, so I was expecting it to be really, really cold because I'd never lived there before, and then it really just wasn't that bad. And so the reason that winters can be warmer sometimes is because you have a low pressure system over the Arctic and a high pressure system closer to the equator. And so what this leads to is air tends to move from high pressure to low pressure. So the air is moving in the northern hemisphere, is pushing towards the north. And so it's kind of preventing all that cold Arctic air from coming down, from sort of settling down over the United States and making the winter cold. And so this winter, this really cold winter, what we're seeing is there's a high pressure system over the Arctic and a low pressure system towards the equator. So the opposite thing is happening. The air is moving from high pressure to low pressure, and it's moving south over the United States. So it's, again, another factor that's going, and this, I don't know how often this cycle changes, but different winters have different pressure systems. And so that kind of dictates what type of, whether it's going to be an unseasonably cold or unseasonably warm winter. So I think my understanding is right now there's a high pressure system over the Arctic, as well as this warping of the jet stream due to a hotter, not really hot, but hotter air expansion. So it's kind of a perfect storm. I hate to use that cliche, but it's a way that both considerations are happening at the same time, with the high pressure and the Arctic warming, so to speak, are happening, where that's what's leading in conjunction. Those two things are leading to the polar vortex that we're seeing.
Okay, yeah, that's pretty interesting. I know we obviously don't have time to go into, but another interesting thing I read in Nature, I think it was, or either Nature Science magazine, they're talking about how droughts, like, even are going to be affected by climate change. I don't remember the specifics because I read this article a little while ago, but they're talking about droughts in California are going to be more common just because there's shifts in weather patterns, which I think would be interesting to look into at some point, maybe exactly what it is. Definitely. But there's just like so many complicated effects going on here that just change not only temperature but precipitation patterns, because you're moving air around in different ways.
One thing that I was looking at was like how climate change might affect the fires, like we were seeing last summer. Like you were just mentioning, there's a drought. If there's a drought going on, if it's really hot out, then moisture is going to be more leached into the air. So trees, for example, are not able to retain as much moisture. So that's what we're seeing in areas like Redding and Paradise, California, where trees were just being quickly burned by fire because they really didn't have as much moisture trapped in them like you would normally have in a tree. So it was part of what was making the fire so destructive, is just this high level of dryness and this really lack of resistance with moisture in these trees.
Yes. So are we good? Are we good on the weather stuff? Should we move on to...
I mean, I looked into hurricanes because hurricanes are fascinating.
Yeah. I definitely would love to hear whatever you got on that.
Yeah. So there's this whole, and I won't get into it too much right now, but there's this whole angular momentum, like physics and calculus derivation about how hurricanes operate, which is really cool. I didn't really get a good grasp on it anyway, so I won't go into it too much, but just in case people are interested, Google hurricane angular momentum or something and try to find, I think the San Jose State had a really cool website about how the physics of hurricanes work. But anyway, hurricanes are essentially these low pressure systems. They start as low pressure systems caused by thunderstorms. And so as these low pressure storms build, what they're kind of doing is sucking in air, because again, like I mentioned a minute ago, air is going to move from higher pressure to lower pressure. And again, Earth's rotation is once again responsible for the way hurricanes kind of turn into that spiral that we're familiar with. There's air coming in towards this low pressure system, and then the Earth's rotating, so it kind of spiralizes these air currents. And so then we start to see the hurricane twist and then turn into this, like the eye that you see from satellite images from way up above. So conservation of momentum, along with the way the Earth rotates, is what causes hurricanes to kind of move towards the poles of the Earth. So a hurricane in the northern hemisphere is going to be pulled towards the North Pole. Eventually, it's also going to be pushed eastward, so you kind of see that as it like comes up towards Florida or New Orleans or wherever, it kind of warps back towards the east at the last minute. So it's just I didn't really understand why that was. Is more conservation of momentum, but there is kind of a mathematical reason for why hurricanes move the way they do. Um, but yeah, basically, so hurricanes, the and I want to talk about how climate change affects them. So just a little bit about what makes them do what they do. So they need to form over basically hot water. So like that's why they form in the on the Pacific side and in the Gulf of Mexico. And this warm air essentially evaporates and moves up these air currents and gets pushed towards the top of the hurricane. So that's where you have the kind of condensation, and that's why you see them. They almost look like clouds on a satellite image. And then as this warm, humid air rises up, the H2O, the water will condense, and that gives the air even more energy to move up further. And so as the air moves up further, you get a higher pressure reduction inside the eye of the storm. And so this speeds up the winds that are coming in, and it intensifies the evaporation that is occurring. And so it's kind of a positive feedback loop. So the more hot water that's available, the more energy that the hurricane can possess. And so if ocean temperatures are rising due to climate change, it leads to hurricanes having more and more energy and more moisture associated with them. So the more moisture kind of leads to this really, really heavy rainfall, like we were seeing last year in Houston. There's a really bad hurricane there, a lot of flooding due to the precipitation that was brought in with that hurricane. And then also you have more powerful winds, and so the eye wall can be more destructive. So the reason the eye of the hurricane, this is just kind of a mini physics lesson. The winds are strongest right at the edge of the eye of the hurricane. So if you think of like spinning, if you have like a spinny chair, you start spinning and you put your arms out and then you bring them in, you start spinning faster. It's kind of the same physics problem that's happening with a hurricane. Is the closer you are towards the middle, the faster these winds are going to spin. So I don't know, it just reminded me of the physics question that I was doing with a student last year. So anyway, the point with climate change is hotter water gives the hurricanes more energy and more precipitation that leads to really heavy rainfalls. And so the amount of destruction that they can cause is definitely positively correlated with climate change.
Yeah, that's definitely something we've just seems like pretty obvious, honestly, in the last like 5 years or so. It's that, I mean, we've had like just a lot of like really big hurricanes come through. I remember when like Hurricane Katrina was like one of the biggest ones ever, and it's horribly just like massive, terrible flooding. But then since then, we've had like a lot more. I mean, I was pretty young, I guess, when Katrina came through, so I don't have like perfect memory of beforehand. But the last few years, it's just been lots of hurricanes, and definitely flooding has been like huge with all of them.
Yeah, I mean, and it was weirdly, I mean, maybe I'm wrong, but Hurricane Sandy just seemed really uniquely far north because I was up in the New York, New Jersey area. And, usually the water up there is a lot colder. And so you wouldn't think that, I said Pacific earlier. I meant Atlantic also. That just came to me. But yeah, so then down in the Gulf, there was Hurricane Irma hit Puerto Rico, and that was really devastating. And Harvey, I think, might be the one that hit Houston last year. And there's just so many more of them, like you were saying. So yeah, definitely. Anyway, so Mike, I think you were going to talk a little bit about renewable energy. Was that the topic that you were looking into?
Yeah, basically. I mean, yeah, maybe to offset some of the sadness that we're getting from this is yeah, I guess we're going to go into, we haven't actually specifically covered, I guess, renewable energy, so it's more like a basics of renewable energy we got here, and just some of the ways that we're currently using them and ways that obviously will need to be expanded in the future if we're going to try and get to, like a more balanced, I guess, of renewable energy versus non-renewable energy. And then, of course, most renewables, we're looking at something that doesn't produce nearly as much carbon dioxide, if any. So it will also get us down to those goals of trying to be neutral, or we kind of need to be negative, honestly, carbon negative at some point in the future. It's actually pretty soon, according to that report that came out over the summer. But Kevin, I have a pop quiz for you, I guess.
Okay.
I'll give you the categories to make this easy, but I'm wondering which, I guess energy they're mostly energy slash just like general categories, I guess, produce the most greenhouse gas emissions. So of the categories we have agriculture, commercial and residential, industry, electricity generation, and also transportation. I guess if you had to guess, which one do you think would be the highest?
I'm gonna go with agriculture because I think I've gotten this question before.
Ooh, ooh,
I could be wrong.
it's rough. No, it's actually the lowest, which shocked me a little bit.
Is it okay?
Yeah,
Maybe I. Yeah.
that's what I thought it would be pretty high too, but we're actually only at 9% of total greenhouse U.S. This is just U.S. greenhouse gas emissions. What are actually tied for first is electricity generation and transportation. I was actually surprised. So they're both about 30% of emissions. So together we're around 60. And transportation, I was actually shocked at how high that is. It's pretty large. And then electricity generation is pretty huge too. Then we have coming in, I guess, third place is industry, pretty general. And then commercial, residential is 10%. Agriculture is about 10% too. So that's just like our general, like those are our categories of emissions. And so I guess mostly I'll be talking about like electricity generation, kind of what we do now. Currently, we have coal is still pretty big, despite the fact that we're kind of going away from it. Honestly, recently, they've been using less coal just because natural gas has been cheaper. So while coal has been decreasing, natural gas usage actually has been going up as well. As long as also with renewables going up, but not at the huge rate that we would want. It's honestly not great. And nuclear generation actually has been relatively stable. I think people have generally an aversion to nuclear energy, but it has a lot of positives, especially because it's just very low carbon dioxide releasage into the atmosphere, which is just like a really great thing to have. But for renewables, I mean, we have about like 4 or 5 different categories. Honestly, I was shocked again because I just didn't assume that this would be the rankings, I guess, of them. But hydropower was actually the highest electricity generation out of all of them.
That is surprising.
Yeah.
I would not have guessed that. I would have guessed solar.
Yeah, me too. I would have guessed solar. Turns out solar is like the smallest, honestly. It was very small. Geothermal is the smallest.
I'm not just 0 for 2. I'm literally
you're failing this class, Kevin.
Yeah,
I'm tired. You're gonna have to retake this in the summer. It's bad. I mean, turns out hydropower actually, I mean, it's been around for the longest. It's the simplest. I mean, so when you think about hydropower, a lot of the time it's in forms of dams. What we're basically doing is we're converting gravitational energy into electricity. Right, so if we have water that's high, we have it flow through something that spins a turbine. That turbine, we use that to generate electricity, and that's it. Simple, actually. It's like one of the simplest ways, and it's kind of been around for a while just because it's so simple. It's like all you need is like a pipe and like a turbine, and then we talked about it previously, but we use an alternator, basically magnets and electric to change this magnetic field to produce electricity. So it's a relatively simple thing. And it turns out most of hydropower is actually on the West Coast. It's mostly like California, Washington, let's see, Oregon, New York, and Alabama have basically all the hydrothermal, or not hydrothermal, it's the hydropower plants.
Yeah. Where's Hoover Dam's in Nevada? Is that still the biggest dam in the country?
I don't think it is. I'd have to look it up, though. I don't think it still is, but we'd have to check.
Hoover Dam is on the border of Nevada and Arizona. I should give Arizona some love there. And it is operational power plant.
Oh, it is? Okay. Yeah.
I'm just perusing the Wikipedia page, but yeah, that's what it looks like.
Yeah. But yeah, I think we're running pretty low on time, Kevin. We might have to wrap it up here.
Okay. Should we do we do a bonus segment that we?
Yeah, that's what I was thinking.
Okay. So how's that working for the listeners?
That's a good question. I guess we're figuring it out right now, but I think that's going to be the end of our KDVS episode. We are going to post this on our YouTube channel later, since we just have more to talk about, because We just
Yeah.
love stuff, I guess. We love talking.
Just love we love talking about the end of the world.
Yeah, we do.
Right.
So if you're listening to this on KDVS, you can go to kdvs.org, go to the schedule grid, and find our show, which is on Tuesdays at 4:30. In the show notes, I'll post a link to our YouTube channel. It should be up, and hopefully I'll try and get it up at the same time, but within a couple of days of this actually being aired, which is Tuesday. So it'll be this plus however much bonus we have, which I feel like is going to be a lot because we didn't get through nearly as much as I thought we would.
Yeah.
So yeah, thanks everyone for listening to this, and thanks if you're going to come and listen to what the bonus episode that we have we'll be recording right now. So that is actually our biggest source of renewable energy. Kind of shocking. So wind energy is another one that's almost the same principle, right? Except we're using the air. It's really yeah.
Can I go back to dams real
Sure.
quick? Because aren't there's some environmental concerns with dams in terms of the downstream. So
Yeah.
if you have a river and you all of a sudden you block the river so you can use the power that the river has, downstream from that river, you're going to cause all sorts of problems for the ecosystem that's dependent on that water. Is that?
Yeah, basically, yeah, you are, as like one of the downsides, there's also apparently shifts in just like the fact that moisture is being released into the environment in like different ways as well.
Mm-hmm.
Since now you have this giant like lake up top instead of
Yeah.
what it used to be, just like a river. So yeah, there are some downsides. It's definitely massively disruptive to just the wildlife there, especially when you're first putting it in, because you're kind of changing everything, honestly, about how this whole river operates. But yeah, I mean, I guess it's one of the trade-offs to having hydroelectric power. It's like very clean, but then yeah, there are some environmental repercussions to it. But I think, I guess people in general think on a net it's like not as big of a cost to pay for.
True. I mean, when you're comparing it to climate change effects from greenhouse gases, I guess it's not as bad. It's still not great, but everything's going to be a trade-off at some point, I guess.
Yeah. And so wind power is honestly same principle. So, the idea is you're using a fluid. You can think of the air as a fluid because it is, and it's the wind basically. Just by the definition of what a fluid is, it is a fluid. Yep. There's not too much debate about that. But basically, you're using wind to turn a turbine. It's the same idea. There's variability. So something that's going to be common with all these is that they are only generated at specific times. So, well, except for hydroelectric, that's actually pretty constant. But a lot of these, if it's solar, be it wind, there's fluctuations in the wind. Sometimes it's cloudy outside, sometimes it's night. So you have a little bit of more variability, and that's one of the problems that I guess we don't really have time to get into, but is how do you kind of store energy so that you can, create a lot of energy during the day maybe, and then store it so you have some at night for when you still need energy, but you're not producing any.
Yeah, there's a lot of research going into improving battery function to really boost solar powers. The ability to use solar power in a more widespread way, be able to store that energy, and that way we can expand the usage of solar power, because solar really is one of the cleanest energies. I guess some of the materials that go into the photovoltaic cells can be kind of toxic, and if they're not disposed of correctly, but overall solar is a really good option.
Yeah.
Again, pending the amount of sunlight that you're getting.
Yeah, solar's great.
Time of day and weather, but yeah.
Yeah, solar, I mean, now that you mention it, it's not the lowest. I had that mixed up. It's just the solar thermal. It's still not the highest, don't worry. You're still not technically right.
Not correct, yeah.
Yeah. But for solar power, we have actually two different ways. I don't know if you've ever seen, like, sometimes there's these, like, big arrays of mirrors, and they shine it at, like, some vessel just to heat something up. A lot of the time it'll be, like, some salt, and you produce molten salt. Yeah, and that's solar thermal energy, where you're not like directly using the light, you're using it to heat something, and then it's more of a traditional thing at that point.
Yeah.
We also have photovoltaic cells, which Kevin just mentioned a second ago, and those are more direct. These are friends that we've been talking about for weeks. They use semiconductors. Basically, anyone remembers from last week, our episode about transistors, we kind of talked a little bit about N and P type semiconductors. This basically will use N and P type just kind of together. And when you have light, you need to design your semiconductors in the exact way this phenomenon will actually happen. But you're able to excite an electron at these higher wavelengths of light. Usually it's, I want to say blue wavelength of like corresponding to blue visible light and higher, but I'm not exactly sure about that. I know there's a lot of work to try and lower that.
Higher wavelength or higher?
Higher, or no, sorry, it's a lower wavelength, higher energy is what I mean.
Okay.
Than blue light. I know tons of work is being done because most of the visible light is actually lower than that. So a lot of the times it's hard. You can't really use all of it. So there's a lot of work being done to try and make it so they operate and use just more of the available energy that goes into these cells. But those, I mean, they're relatively simple. It's pretty great because they go directly from from the light to electricity. So you don't have like a whole lot of complicated system. It's usually just these like weatherproof containers that have these solar cells within them, and you just slap them on your roof, throw them around somewhere, and just let them do their thing. So they're honestly, I mean, they're great just because of the versatility of them and few moving parts. I guess the downsides is they can be expensive to make, but the cost has gone down actually a lot, especially in recent years. So
there's I think there's either tax credits or something like that for residences that install solar power on their roofs. So there's some incentive to. It's still going to cost some money to install them, but between tax credits and then over time, you're spending less money on other sources of, because you have to obviously pay for your electric bill, but that's coming from power companies that are using, whether it's coal or natural gas or nuclear or whatever. If you install solar panels, it's your electricity, so you don't have to. After you initially install them, you don't have to pay for it.
Yeah, yeah. There's actually, I guess there's a lot of variability, but hopefully, at some point there'll be more like incentives to have people use these renewable resources, because it's a great way to get people to adopt things. It happens also with vehicles. So depending on what state you're in, there are places where you can get different tax credits for more efficient cars. And just buying those over, less efficient ones. But it's highly variable, unfortunately. So it depends state to state exactly what the policy is on that. We are running pretty low on time, so we'll go over the last two real quick. Basically, biomass, biofuels. They're pretty similar. It's kind of just using the same ideas. They're like, well, let's use biology, figure out how we can make fuels, essentially, out of, some sort of, like, sugars. Basically, biofuels, a lot of times they're talking about making ethanol from sugar. So fermentation is kind of a way you can go from sugar directly to ethanol. So we're kind of taking advantage of like what bacteria do. It's basically like making beer or wine, whatever alcohol. The bacteria are going to eat essentially sugars, turn them into ethanol. They also produce CO2 as a byproduct of fermentation. So there is that issue. But it's relatively sustainable. People also make biodiesel, which comes from vegetable oils, essentially, which can be run to use like diesel. Most diesel engines apparently should run fine on biodiesel. And biomass is just this is actually what I was mentioning earlier that's kind of related to the permafrost. If anyone heard our permafrost episode, there's something called anaerobic respiration. And that's kind of when bacteria will decompose organic matter into methane and CO2. So biogas is just kind of taking advantage of that. So this happens a lot in landfills. So you can actually collect the gas, probably have to do some separations to a degree to get rid of the CO2. But then you can just use the methane as natural gas, essentially. And instead of venting it to the atmosphere, which it's much more potent greenhouse gas than CO2, it's much more desirable just to burn it, honestly, than to vent it. And so this happens with like landfills, sewage, animal waste. It produces lots of methane, so you can use that as a bit of a just kind of like closed cycle, I guess, of reusing different like fuel sources. All right, I think I'll just keep recording, and then all editing is just going to be fun. Yeah.
Well, let's go back to biofuels. Biofuels are very interesting.
Yeah, biofuels are pretty cool. Yeah, a lot of it is just, so there's like a lot of different ways to do this. And biogas is also pretty general. You can also people do these like pyrolysis, so controlled burning in low oxygen environments of organic matter, which you can kind of use to call biofuels in order to make syngas, so carbon monoxide and hydrogen, and then you can use that to make fuels as well. A lot of this biofuels is kind of just using, like, growing something and then turning it into fuel later. So it's more of a sustainable method. I guess there's also, instead of just extracting like oil from the ground, right, you're also growing something which will consume carbon dioxide. So it's more of a net neutral sort of process in general.
Yeah.
But it's pretty vague, and it can be hard to do.
Yeah, one of the other ones that I think is fascinating is the algae, using algae to make biofuels. There's a million different technologies that go into making it practical and sustainable. But I'll talk a little bit about this place that I visited in Australia, where it was essentially this algae, what do they call it, like a pilot plant to test going completely off the grid to create biofuel. So you have your algae, you're processing them in these fermentation vats, essentially, but all of the energy is being produced by solar power. And so there's no carbon burden, there's no greenhouse gas production, and these algae are being kind of processed and generated so that they can eventually create biofuels. So once essentially the algae is I guess, bred. I don't know. I don't have a good word for it, but once it matures, it has this oil inside of it. And so you let it grow and swell, and then when it gets to the right size, you basically crack it open and take the oil and use it as a fuel source. So it was a really interesting idea and a really interesting place to visit, because there's just this big kind of farm almost in the middle of nowhere. And they were just trying to produce algae that was making useful biofuel. And another technology that can be used to produce the right kind of oil is CRISPR technology. So you can essentially program the genes or program the DNA of these algae to produce the oil that you actually want. And so that's, I think, in very early stages, but something that's pretty promising if you can just genetically program an organism to produce a fuel that you need. I don't think there's a lot of concern about it being like a cruel thing, because I don't think algae is really all that sophisticated of an organism. So, that was something that I learned about, I believe, in a grad school class that I took.
Yeah, no one's concerned about algae rights for sure.
Yeah, not yet.
Yeah, that's true. Yeah, biofuels are interesting. I remember hearing that there were, I don't know how big of a concern this is, but just like, I guess, the area required for like growing a bunch of algae, that like evaporation is like a significant concern just for water levels. Because it's like an artificial lake, I guess, or pond that you're making, right?
Yeah, and you also can't have it be too deep, because if the algae is too far below the surface, it won't get a sufficient amount of solar energy. So that kind of leads to like really flat ponds that are really spread out over wide areas, so that you can get enough solar radiation to all of the algae cells, all the organisms. So yeah, that's a good point. It is kind of land intensive.
Yeah. So as far as, I mean, I guess that's most of the sustainable things I wanted to kind of go over. There's also geothermal energy. It's not like super just well used. It's like less than 1% of the electricity generation in the United States itself. But the idea is you take hot, like water or steam, basically from underground, and there's specific hot spots where you can go. A lot of it's along fault lines, and so most of these are actually in the West Coast. And it's just using steam, hot water, basically from in the ground, using it to either like heat home, maybe. So you can put a heat exchanger beneath your house just to heat up some water, basically, and then pump it through your house to warm it, or just as a source of warm water, or you can use it to turn a turbine, generate electricity. But it's pretty small. It seems like it's probably just like not something that's feasible to do at like a huge scale, but it's kind of nice, I think, is the best way to describe it. It's like pretty cool. But it's not something that'll actually just like, it's not like a game changer. It's not like a thing that can be used, I think, widely enough to like kind of become a major source of energy. One thing I
Right.
did forget to mention though about hydropower. Did I mention anything about tides? I don't think I did.
No, tidal is really cool too.
Yeah,
It's kind
so
of the same idea, right? It's you use the tides coming in and out to again move a turbine, which is pretty much the
yeah.
name of the game in any kind of electricity generation.
Yeah, exactly. It's just like, well, instead of having to rely on basically like a damming something, you just put this turbine in the ocean, put it deep enough that I guess at the right depth where tides going in and out will turn this turbine, and that current just is always basically going. So you can get pretty consistent energy from that as well. Uh,
Which electricity generation techniques don't use turbines? I'm trying to like solar
Not
doesn't really
many,
use
yeah. So
turbines.
solar
Like
doesn't use turbines. Um,
it might be
that's
it.
mostly.
That's interesting.
Yeah, I mean nuclear energy doesn't use Wait, no, they do. Never
I think it
mind.
does, yeah. You
Yeah,
use the heat
yeah,
release from the
yeah,
nuclear
yeah. You just use
reaction
it to
to
make steam. I
make
mean,
steam.
that's
There
the
we
name of the
go.
game is making steam. That steam
Hmm.
cycle has been paying off for hundreds of years.
Yeah, a couple hundred years now.
uh,
I guess no. I mean, I guess you don't have steam in like a dam, in like a
no,
uh, hydroelectric, but it's still a turbine.
yeah, I mean, yeah, almost all. They really can only think of like photovoltaic cells being the only common, I guess, energy generation usage that doesn't turn a turbine of some sort.
Right.
It's actually pretty crazy when you think about it like that. Um,
Yeah. I guess, I mean, you can make the argument like in a car with gasoline, you're not turning a turbine so
yeah.
much, but you're still powering all the piston movement
Well,
to
one
make
thing
the engine move.
that's not commonly used, fuel cells go directly from chemical energy to electricity. So those
Okay.
actually they're not very common, but fuel cells, whether it be like solid oxide fuel cells or some sort of methanol fuel cell, something like that, those all go actually directly from chemicals to electricity. So in general, they're more efficient.
Yeah.
But they're not really used just because of like the materials cost is a little high most of the time because they have really fancy either electrodes or cathodes, or
Hmm.
electrolytes or cathodes and anodes. Some part of it is usually like just ridiculously expensive, and then
Hmm.
it makes it a little hard to economically justify. But that is another one, I guess. But yeah, it's more niche as well.
I could have sworn we talked about fuel cells on a episode. I think it was an early one a
Yeah, I
long
think
time.
so. Yeah, we talked a little bit. I mean, so I did a little bit of research on or not hydrogen, solid oxide fuel cells. So I think we brought that up a while ago.
It's probably in our battery episode.
Yeah, I think so. Just because
Very
fuel cells are basically batteries, but
yeah.
instead of storing energy, that you have to provide the chemical energy. But there's still the same process going on where you're take like there's redox reactions, basically reduction and oxidation happening at either cathode is reduction, anode is oxidation, and you have movement of ions, and the movement of ions is coupled with electrons moving that you use to generate or you use to power something.
Yeah.
So yeah, it's a similar idea. But yeah, they're not very commonly used, unfortunately, but they are pretty cool.
Definitely. Um, so I guess other than your renewable section, the only thing I had to talk about was how we measure climate change. Do you have anything else to add on renewables?
Uh, no, not really. I mean, so I had a little bit of stuff about livestock and how they're terrible. I think we can save that for another episode, though. Essentially,
Definitely.
livestock, they emit a lot of stuff, and it's awful. Um,
Yeah.
but yeah,
They just
maybe and not enough to go into a ton of detail now, but maybe enough we can save for later.
yeah. Um, so we kind of hinted at some of this earlier, how global temperatures are rising and sea levels are rising, et cetera. But some of the ways that we measure these things are really actually fascinating. These techniques that are used. One of the main ones is measuring the composition of air bubbles that are trapped in either ice cores or sediment cores. So sedimentary rock, if you kind of think back to your geology units in middle school science classes or whatever, sedimentary rock is the one that forms in layers. And so each further layer is that as you go successively downward is older, is from longer ago. And so there are various ways to kind of date how long or how old these samples are, which I'll talk about in just a second. But the thing is, and it's the same thing with ice, by the way, is like glacier formation happens over years, and so each layer is older the further down you go. So these air pockets that are trapped or these air bubbles that are trapped inside the ice or inside the sedimentary rock. If you measure the content, you can kind of measure carbon content, for example. And so there's a trend that older rocks, the air bubbles from older rocks or older ice cores, contain less carbon. And so that's kind of one way we can kind of paint the picture of we have more carbon now. We have higher temperatures now. So it's another link that we can demonstrate. Another thing that I thought was really cool was there's these water these isotopes of oxygen in water. So in really old ice, I've mentioned that it's old ice already, but basically you have these isotopes of oxygen in the water, and if you measure the amount of that oxygen, it's dependent on temperature. So you can correlate the amount of that isotope that you find in an ice sample with how hot that year was that ice came from. And so if you can kind of cross-reference that with how old this ice core is, you can kind of show, okay, so the temperature was on average this high this long ago, and this high this long ago. And you can kind of create this timeline or this archive of weather data, of climate data, and kind of show how the temperature behaves over hundreds of years. And so that's kind of one way, because when scientists talk about, oh, wasn't this hot back in, 1200 AD, it's like, how could we possibly know that? And so this is one way that we can kind of measure how that is, because it's not like the old civilizations in the Dark Ages were putting thermometers out and writing down the measurements every day. We didn't have the scientific initiative that we have now, where we're literally keeping painstaking logs of temperature every single day. So this is one of the ways that scientists have figured out to get around that. As far as
that's super clever. So they use oxygen isotopes to get temperature. But then how do we get how do we know how old it is? Is it carbon dating?
Yeah. So carbon dating, if you have something organic in there, is obviously really useful. You can also, one of the really cool ones is you can link it to volcanic eruptions, because those are things that were pretty well documented. For instance, in 1783, this mountain called Laki, I think it's called, Laki, erupted. And so there's really high sulfur content in that ice. And so that ice is really obvious. When you find really high sulfur content, okay, this is either in 1783 or soon after that, because there's tons of sulfur in the air. And so that's one way that we can do it. It's just kind of tying it in with historical events. There's also, I believe, the rate of glacier increase, the rate of glacier movement can help kind of at least estimate how old the ice is, because glaciers move at a fairly constant rate. I guess it can change depending on temperature, but I guess that's one way where, the further down a glacier layer is and how far it moved can kind of help you determine how old it is. I don't have great specifics on that, but and then let's see, horizons formed in conjunction with historic events. Yeah, so the other one, so the volcanic eruption was really cool. The other one was when there were a lot of nuclear tests back in, I guess that would be the 1940s or 50s. Those isotopes are trapped in ice layers also. So those are other things that you can use to say, they definitely detonated a bomb at this time back in 1950, whatever. So we know that this layer of ice is from 1956 or however that works. And the same logic can apply to sediment cores also. So it's really cool how they're kind of finding creative ways to figure out how old stuff is and how the climate looked back then.
That's pretty crazy. Can you imagine if we all died and then someone came in here 10,000 years later or something and started drilling for ice, and it's like, whoa, what happened?
What were they doing?
Yeah, they did some crazy stuff. This is insane. That's really cool though. Volcanoes are interesting. That's because they're such colossal eruptions are they're literally earth changing. We should do some episodes about volcanoes. That sounds fun.
I like that idea. So the other thing that we measure is obviously we care about temperature and global temperature, and so there's a lot of different ways to measure the temperature around the Earth. I think buoys have thermometer type devices on them that can help determine temperature at various points in the ocean. But satellites also help measure temperatures, and they have devices called radiometers on them, which I'm going to say the sentence and I'm going to try to explain it, but they measure spatial power of electromagnetic radiation. So it's different from photometry, which I don't know if we've talked about, but photometry measures number of photons essentially. So how intense a light beam or whatever kind of electromagnetic radiation beam is. This kind of measures how spatially powerful, I guess, electromagnetic radiation is, which can be correlated to temperature. What did I write here? Oh yeah, that was all I had on radiometry. And then other things that we want to mention are like precipitation. The way that we measure precipitation in the year is so much simpler than I thought it was. I was thinking like they had satellites and then imagery and all this, and really it's just like a bucket with lines up. Like
I was going to guess, do they just use a cup? It's like
pretty much, yeah, just like a graduated cylinder. It's not as exciting as that is. I'm sure there's other ways, but yeah, that's why don't fix it if it ain't broken.
Yeah, I would just love it when you think something's really complicated. It's like, no, it's just simple. It's like it works.
Yep.
Okay.
I believe I was gonna read off the things that we measured. So temperature, precipitation, other variables that they measure to determine climate. Overall climate is humidity, wind speed, air pressure, cloud cover, solar radiation. Those are some of the things that they look at to kind of determine what other effects might be happening that can determine how the climate's behaving. So that is all I had on climate change measurement. It was a good little bonus segment there. I liked that.
Is there anything you want to say?
Thanks for listening, everyone who stuck around for the bonus segment.
Yeah.
We're going to try to do more of these in the future. So hope you enjoyed it.
Yeah, it seems like we just go on, or sometimes we just cut ourselves off, and then I definitely have like a few pages of notes where it's just like, well, I guess we'll never get to that. It's nice to be able to get to everything we actually looked at, because usually look at a whole bunch of stuff and then throw half of it out and then find some interesting stuff after that.
Yeah.
But I think we're going to wrap it up there. Thanks everybody for listening. This has been Science in Context. If you're listening to this, that means you're on YouTube. So if you want, you can subscribe to our channel and be notified when we start posting more videos. Or if you want to listen live, you can go to kdvs.org, listen to our show live. It's a shorter version. It is on at Tuesdays at 4:30 p.m. Pacific Standard Time.